Pour commencer, ici c'est la conférence du médailliste de CRM ACP David Medal, qui a gagné le prix de l'année 2022. Il me fait plaisir de présenter David Medal, que je connais depuis, maintenant je ne suis pas certain, David, c'est 89, je pense. Oui, 89, c'est quand il est arrivé à l'Université de Montréal. Okay, I will switch to English because the talk will be in English. So it's a pleasure to introduce David. Came in 1989 to the University of Montreal after a PhD at Chicago with John Rosner as his professor, and postdoc at UBC, followed by another postdoc at Recipient in Germany, where he worked with Roberto Pecce, who is very famous for this Pecce-Quinn symmetry. He was there for 3 years ago, and then came to the University of Montreal. David is one of the best-known theoretical physicists working on the physics of B meson decay. So he will explain to you in mathematics what is B meson and what is the decay and all that, right? But these decays are very important for our understanding of CP violation or equivalently time reversal, even though you believe in the CPT theory, CP back, so is Q. And that affronts the general public more actually. David has written over 150 tertiary publications on particle physics with over 12,000 citations. And he was recently, he won the particle physics medal of the CAP, called the Vogt medal, maybe 5 years ago, something like that. And on top of that, he was inducted into the fellowship of the Ring, the Society of the Royal Society of Canada, the fellow of the Royal Society of Canada. Ending on a lighter, in 1993, David wrote a paper which generalized 3 parameters which describe low energy particle physics of the B decay. And this paper has 250 citations for its own. Right? The parameters were called S, T, and U. And it was Peskin and Takeuchi who developed it. They make 3 assumptions, very basic. No new gauge boson, certain couplings are very small, and new physics appears at a very high energy scale. And with those, they can parameterize all the low energy physics. But they've been, along with collaborator student Maximic and Cliff Burgess, who has won this medal in the past, generalized 3 more parameters. Okay? And now you have X, T, and U. And then you thought, how these stupid parameters? And then you went the route of the Egyptians, the Phoenicians, and the Babylonians, alphabetic.
So thank you. Did you already look at my slides?
Did I think that?
The talk's going to be at least 10 minutes shorter than that. So thank you very much for the invitation. Well, thank you to the CAP and to the CRM for the award, and thanks for the invitation to give this talk. So what I'm going to tell you today is I'm going to summarize some of the things that I've done, for which I was awarded this prize. And as you can see, the title of the talk is The Search for New Physics. Now, in particle physics, the ultimate goal is to find the theory of everything. And by the theory of everything, I mean a mathematical model or a mathematical framework in which we describe all of the particles of the universe and all the forces with which they interact together. And this will, if ever it's found, this will describe physics at all energy scales, which will enable us to understand basically the evolution of the universe. That's why it's called the theory of everything. Now, I know that most of you, I know that all of you, you're mathematics people, and to some extent, I don't know to what extent you know physics, and I suspect that some not at all, and even those who know some physics probably don't necessarily know particle physics. So I'm going to try to give you context into what I've done. And to make, so I'm a physicist. I mean, technically the prize is for mathematical physics, and I'm on the physics side of the mathematical physics. The main mathematical tools that I use are group theory and field theory, and I'll show you how they enter at different places. The main point is that in order to find this theory of everything, in order to relate these things, that requires symmetries. And you'll see that symmetries appear at several occasions, at several points during this talk. Okay. So what I'm going to do is, here's a quick overview of the subjects. I'm going to really briefly talk about different energy scales. And then, since I said that the theory of everything wants to describe all the forces and the particles, I have to tell you what the forces and the particles are. And then I'll describe the standard model, which is the progress which we've made towards this theory of everything. Problems with the standard model, and then I will finally get to what I've done, just to say the work that I've done for this award, which is basically studying physics beyond the standard model. Now, another idea which will come up often is the idea of energy scales, different scales of energy. And when particle collisions take place at a certain energy. And obviously, they can take place at various different, different energies. And here's basically, this is a log scale. It's a little hard to read, but basically, we live here. This right here is 10 to the 0. In GeV. So the mass of the proton is 1 GeV, and this is roughly where we live. But I'm going to talk about the weak interactions and the weak scale, and the weak scale is at about 100 GeV. I'll remind you of these numbers as we go along. So we live here. The weak scale is about here. That's about 100 GeV. There are currently experiments that taking place at CERN in Switzerland, and those take place at 1,000 to 10,000 GeV, like around here. But at the beginning of the universe, we were at what's called the Planck scale, and that was 10 to the 19th GeV. And so, as you can see, it's quite far away. Anyway, so these are the energy scales that I'll mention along the way. But just to give you an idea of the various different scales that I'll be talking about. Okay, so let me first start telling you about the forces. There are 4 forces in nature, as far as we know. There's electromagnetism, there's gravity, there's the strong force or the nuclear force. And the strong force basically holds protons and neutrons inside nuclei, or it holds quarks inside the protons and the neutrons. And then you have the weak force, and the weak force is responsible for radioactivity and certain decays like beta decay. Beta decay is the decay of a neutron. The neutron decays to a proton and an electron antineutrino, and that's due to the weak interaction. There are these 4 forces do not have all the same strength. And at our scale, at 1 GeV, basically, as far as if we measure them today, what we'll find is that the ratio of strengths, if alpha S is for strong, alpha S is the strength of the strong interaction. If we call that 1, then the strength of the electromagnetic interaction is about 100 times smaller, right here. The weak interaction is about 1,000,000 times smaller. And the gravitational interaction is, as you can see, 10 to the minus 39. So very, very tiny. And in fact, I'm not even going to talk about it anymore. Okay, so I mention it, but it's not important for.
I thought that uniting gravity would quantum theory was the main issue.
Sure, no, it's one of the issues, and I'll come to that at the very end.
That seems to be avoiding the question.
That's right. So, okay. So let me just remind you or tell you about the four forces. Electromagnetic. What one learns at the undergraduate level is that electromagnetism is basically described by Coulomb's law. Here you can see F is equal to F is the force. The force is Q1, Q2 over R squared. So in other words, if you have two particles, two charges, Q1 and Q2, they interact in another force law. The classical view of this is that one of the charges, let's say Q1, creates an electric field, and the second charge, Q2, interacts with this electric field. And that's the classical view. Now, this electric field, of course, has energy, as we all know. And in quantum mechanics, energy is quantized. And so that when you look at this from the point of view of quantum mechanics, the smallest packet of energy, the smallest quantum of energy, corresponds to a particle, which is called a photon. So in other words, this electric field is in fact made up of a cloud of photons. If you go a little bit further, and you go to field theory is basically combines quantum mechanics and special relativity. And within field theory, these forces are described by things called Yang-Mills theories. And there the key point is that the Lagrangian obeys a symmetry. And the symmetry is related to a Lie group. Now, Lie groups, or I should say technically Lie algebras, have generators. And within these Yang-Mills theories, for each generator of the Lie group, there's a massless spin 1 gauge boson that mediates the force. So in other words, there's one particle and it emits a mediator, and the other particle absorbs the mediator, and that creates the force. Okay, but the point is that there is one gauge boson for each generator of the Lie group. In the case of electromagnetism, it's described by the group U1. U1 has one generator, so it has one gauge boson, and that's the photon. The photon has mass 0, as it has to, according to this. So it's massless, which means that its range is infinite, and it couples to electric charge. So any particle that has electric charge feels the electromagnetic force. And this is QED, quantum electrodynamics. The strong force is also described by a Lie group. This time the Lie group is SU3, SU3C for color. SU3 has 8 generators, which says that there are 8 gauge bosons, and these are called gluons. Gluons from glue. And so there are 8 mediators of the strong force, 8 gluons, and the charge of the strong force, just as the electromagnetism has the electric charge, the strong force has the strong charge, which is called color. It's just a name. Color. And since the fundamental representation of SU3 is a 3, there are 3 colors. And this is QCD, quantum chromodynamics. And here, even though the gluon is massless, the range of the strong force is microscopic. It's not infinite like the electromagnetic force. And that's because the force actually grows with distance. This isn't technically correct. This is just to kind of illustrate. So just as the electromagnetic force decreased as the distance increases, the strong force increases as the distance increases, like a spring. So if you have 2 colored objects that are interacting via the strong force, you can't pull them apart. And this is called confinement. And what this means is that any we can't see any colored objects free in nature. They're all confined to live with other colored objects. The weak force is related to the group SU2. SU2 has 3 generators, and 3 generators means that there are 3 gauge bosons, and these are the W plus minus, and the Z0. And the weak charge is called weak isospin. So that any particle that has weak isospin feels the weak force. And just to do a note that in the middle of the 20th century, we only knew about the W plus and minus. We didn't know anything about the Z0. That was found later. I'll mention that in a couple of slides. Yes. Oh, I jumped a page. Okay, I was wondering. Right. So the W and the Z are not massless, but they're supposed to be, according to what I said about Yang-Mills theories. You should have massless gauge bosons, but the W and the Z are very massive, 80 and 90 GeV. Remember, the proton is 1. So these are much heavier than the proton. But the point is that they're not massless, which means that this symmetry of SU2 has got to be broken. It can't be a good symmetry. But okay, and so we have the symmetry group must be broken, and I'll come back to this later.
The force is not being affected, it's the potential that's.
Okay, very good. Very good. I mean, this is, as I say, this is not rigorous. This is just meant to illustrate what's going on. Okay, so those are the 4 forces. Let me now talk about the particles. All matter in the universe is made up of fermions, spin-a-half fermions. And these can be classified and distinguished according to their charges. And when I say charge, I mean electric charge, weak charge, strong charge. In other words, electric charge, color, and weak isospin. So these particles can be distinguished according to their charges and can be further separated into 2 types. Leptons, which don't have color. In other words, they don't feel the strong force, and quarks that do have color. Now, in quantum mechanics, angular momentum is quantized, and in particular, spin is quantized. And what this means is that if you have a spin-a-half particle, the spin-a-half particle has 2 components, spin up and spin down. And the point is that if you choose some direction, the z-axis, let me say that the z-axis is pointing vertically, the spin is either points in the direction of the z-axis or anti in the other direction. So it's quantized along this axis. For a particle, it's convenient to choose this axis to be its direction of motion. So a particle for me is going to my right to your left. So then its spin is either parallel to the direction of motion or anti-parallel to the direction of motion. If it's parallel, we call that right-handed. If it's anti-parallel, we call that left-handed. Okay. Why do I mention this? Well, experimentally, it's found that the electromagnetic and strong forces couple equally to left-handed and right-handed particles. They don't care whether this is called the helicity, left-handed and right-handed. They don't care whether the helicity is left or right, but the weak interactions couple only to left-handed particles. That's an experimental fact. So in other words, left-handed particles have a weak isospin. In this case, it's a half. And right-handed particles don't have a weak isospin. They don't feel the weak force. Why? I don't know. It's just the way it is. But our theory of everything would ideally give us an answer to this. So here are the particles.
With
Yeah.
the shorter particle as is left-handed or right-handed, could any particle be either one, or Some particles are left-handed, some others are right-handed.
No, any spin a half particle in general has both left-handed and right-handed components.
Okay.
So you'll see in fact,
And two representatives.
yeah, in fact, well, you can just see it right here. That, so for example, the leptons are particles that don't feel the strong force. There are two types, charged leptons that have a charge -1 and neutral leptons that have a charge 0. The charged leptons are the electron that you're all familiar with. Then there's the muon and the tau, also charged -1, that are just like the electron, just heavier. For each charged lepton, there's an associated neutrino. So the electron has its own neutrino, nu e. The muon has its own neutrino, nu mu, and the tau has nu tau. And so these form 3 generations of leptons of increasing mass. So you have the nu e and the e, and the left-handed components form a doublet under the weak force, the weak SU2. The muon and the tau, you also have the left-handed doublets, whereas the right-handed guys are singlets. Now you'll notice that there are no right-handed neutrinos. In the standard model, the original standard model, neutrinos were purely left-handed. And that's because when it was first constructed, it was thought that the neutrinos are massless. So only massless particles can have one helicity. And so basically, according to the standard model, the neutrino should be massless. For quarks, there are again 2 types. There's you have quarks that are charged 2/3 and quarks that are charged -1/3. 2/3 are quarks U, C, and T, up, charm, and top. And the -1/3 quarks are down, strange, and bottom. Once again, they can be placed into 3 generations of increasing mass. The left-handed up and down quarks form a doublet. Charm and strange doublet, top and bottom form a doublet. And we have the right-handed quarks. And here you have to remember that all of these quarks come in 3 colors. So I've written six different so-called flavors, but in fact there are 18. There are no free quarks, once again, because the quarks have color, so they have to be confined. And so they are only found in nature coupled with other quarks. There are 2 types of particles that do this. You have mesons, which are formed of a quark and an antiquark. Those are, so for example, the pi plus meson has a U and a D bar. You can quickly check that the U has charge 2/3. The D has charge -1/3, so the D bar has charge +1/3. And so that forms +1. And you also have baryons, like the proton, which are formed of 3 quarks. UUD, you can quickly check that that's charged, that their charges add up to 1.
Sorry, I mean, do the quarks, they can also be left-handed or not? Only the combinations.
The quarks themselves can be left and right-handed, but in mesons, well, the mesons themselves are spin 0 or 1, so they don't have left or right-handed.
Okay.
But
Sorry again. So these colors can come just by themselves, but you don't have to be all 3 together. They don't need to.
okay. The mesons and the baryons must be neutral in color, which means that the mesons, you combine a color and an anticolor, and with the proton, with 3 quarks, they have to have all different colors. So blue plus red plus green is equal to white. Okay. And the weak interactions between leptons or quarks is due to the exchange of a W boson. And the W boson is charge 1. And if you look at the particles that feel the weak force, you can see we have doublets, nu E and E, or U and D. And you can quickly check that the difference in charge between the 2 particles, nu E and E minus, is 1. Just as the difference in charge between the U and the D is. And that's due to the fact that you can turn one into the other through the exchange of a W, which is charged 1. Okay, so at the beginning of the 20th century, we knew of 2 forces. We knew, I mean, once again, I'm putting gravity aside. We knew of electricity and magnetism, and they were 2 different forces. But Maxwell and basically Maxwell and Einstein, that gave us Maxwell's equations and special relativity, told us that in fact these 2 forces, there's a symmetry that relates them. The symmetry is called the Lorentz symmetry, and they were then unified into a single force, which we now call electromagnetism. In the 60s and 70s, there was a similar unification, or at least I should say a proposal to unify the weak and the electromagnetic forces into a single force called the electroweak force. And here the idea of energy scales comes into play. At low energies, the weak and the electromagnetic forces are clearly different. The photon is massless, the W and the Z are very, very massive. But the idea is that at high energies, at the beginning of the universe, for example, but anyway, at high energies, the symmetry is good. And the W and the Z are massless, like the photon. And there's a symmetry that relates them. But as you go down in energy, at some point, the symmetry is broken, and the W acquires a mass. And then we have the 2 different forces that we see today. So if you think about the evolution of the universe, at the beginning of the universe, there's a huge amount of energy. It's the Planck scale. All collisions take place at 10 to the 19th GeV. It's very high energy, and the symmetry is good. And then as the universe expands, it cools, and then the average energy decreases, and at some point, you reach an energy level where the symmetry is broken. That's called the weak scale. And above the weak scale, the symmetry is good. Below the weak scale, the symmetry is broken. Okay, and the model that unifies the electromagnetic and weak forces into a single one made a prediction. As I said, this was proposed in the 60s and the 70s. Before then, all we knew about was the W plus and minus. We know basically there was 1 particle, or if you prefer 2 particles, the W plus and the W minus. It predicted that because the symmetry group that describes the electroweak force is SU2, which has 3 generators, there's got to be a 3rd boson. So they predicted the existence of the Z0. And they also said that if the mass of the W is 80 GeV, the mass of the Z boson should be 90 GeV, 91 GeV. And in fact, in 1983, that's when I was still a graduate student, the Z0 was discovered at CERN and through this process, and its mass was 91 GeV. So this model made a prediction that was confirmed. Right. So the standard model of particle physics, which is where we are today, it basically includes this electroweak force, or this electroweak theory, and QCD, which is the strong force. So it describes these both forces, and it's made lots and lots of predictions, almost all of which have been confirmed. Right. For a number of years, there was only one thing missing. In order to break this electroweak symmetry, in other words, as I say, at high energies, you have a good symmetry, and at some point it's broken. And I never told you exactly what that means, breaking the symmetry, but okay. But in order to break the symmetry, you need a new particle. And the particle that breaks the symmetry and also gives masses to the W and the Z and to fermions is called the Higgs boson. And for many years, it was the only thing that was missing. And it was found in 2012. It was discovered at CERN with a mass of 125 GeV. If you recall, I said that the weak scale is of order 100 GeV. It's the mass of the W and the mass of the Z. It's also the mass of the Higgs. So that's the weak scale. Okay, as I say, the standard model has made lots and lots of predictions, and they've almost all been verified. There's no doubt it's correct. It's kind of like Newton's laws. Everyone learns Newton's laws in classical mechanics. Newton is correct. But the thing is that Newton's laws don't apply everywhere. They don't apply if you go very fast. They don't apply if you go very small. So if you go very fast, you have to use basically you have to go beyond Newton's laws. So Newton's laws are not complete. You either have to modify the laws towards special relativity or towards quantum mechanics.
Right, but you would say that they are correct as opposed to extremely good approximations.
I think we're arguing about words. I mean, I'll give you a real physics answer.
Yeah.
Whatever. Okay. Right. Right. Similarly, the standard model has made tons of predictions. They've been verified. There's no doubt that it's correct. However, okay, and it's in fact one of the greatest achievements of modern physics, just to develop a model. And usually what happens is experimentalists make measurements, they get results, and then the theorists go and try to explain the results. It's rare where a theorist actually comes up with a theory and makes a prediction, and then the experimentalists go out and verify it. It happens, but that's rare. Okay, but there are a number of reasons to believe it's not complete. First of all, there are what I call philosophical reasons. There are a large number of arbitrary parameters. The standard model doesn't explain why the mass of the proton is 1 GeV. Doesn't explain why the mass of the electron is whatever it is. There's lots of unanswered questions. The standard model doesn't tell us why the weak interaction couples only to left-handed particles. And not all forces have been unified. The gravity has still not been included. Now, you might argue that these are philosophical. There's no reason a priori that the theory of everything must absolutely do this. You know, maybe it just is what it is. But there are measurements which the standard model can't explain. So neutrino masses is one. I mean, I mentioned in passing that the standard model predicts that the neutrino should be massless. And in fact, we now know that the neutrino is massive. So in order to explain it, you have to go beyond the standard model. Mm-hmm. Dark matter. The most prevalent form of matter in the universe is dark matter. We haven't found it yet, but there's lots of there are many indirect indications that exist that indicate that it does exist. Clearly, something is going on, and the most plausible explanation is dark matter, except for this one.
Dr. Gill's question, I would say what you've just said shows that the standard model is undoubtedly incorrect.
Okay. Okay.
You will answer whatever.
And there's also the baryon asymmetry of the universe. I'll explain this in a little bit more detail in a second, but basically there's a question: why is the universe composed almost entirely of baryons and we see no antibaryons? Standard model doesn't explain that. And in order to go beyond the standard model, for these reasons, we believe there must be physics beyond the standard model. And basically, all research in particle physics today is geared to the finding this new physics. And in fact, my research has basically focused on the search for this new physics. Now, let me give you tell you ways in which a theorist can search for new physics. I mean, so basically there are lots of ways, and I do what's called particle physics phenomenology. And phenomenology, there are close ties between theory and experiment. I don't do experiments. They don't let me touch but I do talk to experimentalists, and I pay close attention to the results. And so from a theoretical point of view, there are various ways that we can search for new physics. So first of all, I can invent a model of new physics. And then given a model of new physics, the question is, how do we search for it? One way to search for a signature of this new physics is that the new physics model contains new particles. So the experimentalists can go out and look for these new particles. And so that's the direct search, the direct signal of these new particles. Another way is through indirect signals. That is to say, earlier I described the electromagnetic force as somehow a charge here emitting a photon and being felt by or received by another charge here. And so this is, in fact, whenever I talked about the gauge bosons, I talked about mediators. So one can imagine that there's, in addition to the photon and the W, et cetera, there are new physics particles that are mediators of a force or of a process, but you don't actually produce these new particles, but they enter in interactions. And so these are indirect signals. So basically what you want to do is to make a measurement and see whether it agrees with the prediction of the standard model. If it doesn't, then you know something else is going on. That's right. So a signal, the signal of an indirect signal of this new physics would be a discrepancy between the measured value of a process and its prediction in the standard model. Another thing that we can do is to just look at the experimental measurements and see how they constrain different new physics models. Here I talked about indirect signals of new physics. I said I wanted to compare the measurement with the standard model prediction. That assumes that we know what the standard model prediction is. And we don't always. Sometimes we actually have to work it out, and I've done that as well. And this is the most fun one, is that every now and then there's an experiment that disagrees with the standard model. I mean, apart from dark matter, and well, even dark matter, there's some measurement that disagrees with the predictions of the standard model, or which is unexplained by the standard model. So then, and that's why I say it's the most fun, is you invent new scenarios that could possibly explain it. And then, you know, once again, if you have a new physics model that could possibly explain it, then that comes back to, that comes back to point number one here. You have to find ways of verifying it, or since we're physicists, of basically ruling it out. And basically, I've done all of these things. So now in the rest of the talk, I'll give you examples of the things that I've done over the years. I've been doing this for some 30-odd years. So I'm just choosing a couple of things. In the 1980s, superstrings were popular. In fact, it was around then that superstrings were invented. So at the time, the superstring theory that was most talked about was something called the heterotic string theory. And the idea was that at the Planck scale, the gauge group was E8, or maybe it was E8 cross E8. I don't know. But then it was broken, and then below, at energies below it, and now I'm not talking about low energies. I'm talking about, we have the Planck scale, and then you go a little, Planck scale is 10 to the 19, and then you go a little bit below, let's say 10 to the 15 GeV, and that's called the GUT scale. GUT is grand unified theory. That's when all the forces, or not gravity, the other forces are unified. Other guts, so basically the idea is that this E8 cross E8 is broken to E6 at the gut scale. And then it's subsequently broken to something smaller at low energies. Other grand unified theories that had been studied were SU5 and SO10. Both of these are contained in E6. So E6 contains SO10 cross U1. And SO10 itself contains SU5 times another U1. Remember, each U1 has one generator, so there's one gauge boson associated with it. The gauge boson associated with the U1 here, SO10 cross U1, I've labeled it psi, so this is a new Z boson, or Z prime psi. And the U1 associated here with SU5 cross U1 is called chi. So E6 has these two new neutral gauge bosons. And so, well, Manu mentioned that my advisor was John Reisner, and so in my last year of graduate studies, we looked at Z prime bosons in E6. And basically, we said that if, the E6 exists here, and then you come down in energies, and if there's one new Z boson, Z prime, one new Z prime at low energies, it could be a linear combination of the Z psi and the Z chi. So it's right here. The Z of theta is Z psi cosine theta plus Z chi sine theta, just some linear combination. And we looked at it, and we studied various properties. Basically, we looked at the present, at the time, the present experimental measurements, and we were able to put constraints on this new particle. And also we were able to make predictions for how it would affect future measurements. So basically, when experiments went and looked for these new particles, when they looked for a Z prime, a new Z prime boson, they use our formalism, so that's fine, and so that was fun, but unfortunately, no new Z prime bosons have been found.
The word mixture here, is it something different from what we call superposition in quantum theory? What do you mean by mixture?
What I mean is that it's just it's simple. It's even simpler than that. You know, you have X and Y, and then you have a vector. So just a vector. So this vector is X cos theta plus Y sine theta.
Good enough.
Just that.
Yeah.
Just that.
The level of the quantum fields, not the state.
Okay, yes, no, I agree. It's at the level of the quantum fields. Yes. Anyway, as I say, no Z prime bosons have been found. I like to joke with my students that basically 95+% of the things that I do are wrong. I mean, that is to say, I make predictions and they're not, well, they're ruled out.
Well, not being found doesn't mean it don't exist. We didn't find anything.
Okay.
So,
But so, as Manu said, the subject for which I'm probably best known is CP violation in the B system. So the idea is simply that, okay, here's the motivation. The Big Bang released a huge amount of energy. This energy is converted into matter. And typically, it's converted into equal amounts of matter and antimatter. A photon will turn into an E plus and an E minus. The E minus is matter, the E plus is antimatter. So at the beginning of the universe, it was 50-50, matter and antimatter. Today, all we see, to a very good approximation, all we see is matter. So the real question is, where did the baryon antimatter go? Sakharov said that the only way to, well, in order to explain this, three things are necessary. First of all, baryons must decay. So you must have baryon number violating processes. Secondly, you must have CP violation. CP is the symmetry that relates matter and antimatter. So if CP is conserved, then even if the baryons decay, the baryons will decay into something, and antibaryons will decay into some equal amounts, and you're going to still have the same amount at the end. But if CP is violated, you could imagine that the matter decays more slowly than the antimatter. So the antimatter decays away, and you're still left with some matter. So there's got to be CP violation, and you must have, and all these interactions must be out of thermal equilibrium, because otherwise a particle would decay and then it would undecay. And now, what's the connection with the standard model? The only possibility is CP violation, and that's because at low energies, yeah,
Is that correct said that it must be at least one of the three or all three of them?
all three. All three. Now, in fact, CP violation has been observed at low energies. In 1964, CP violation was found in kaon decays. I won't go into the details. I'll just say that CP violation was observed, and the standard model explanation of this is that there's a complex phase in the CKM quark mixing matrix. CKM stands for Kabibo, Kobayashi, Maskawa. Kobayashi and Maskawa won the Nobel Prize for this matrix. I'm not going to go into the details. I just want to say that you add one parameter in the standard model, this complex phase. And the reason I put explanation in quotation marks is because you've got one new data point, one new parameter. That's not an explanation. I mean, you can. It's a description. In order to turn this into a real explanation, though, you have to take this and make predictions, and then test those predictions. And this is what was done. Basically, this explanation, and I'll show you on the next slide. This explanation predicts. Here, there's CP violation observed in kaon decays. If true, if this explanation is correct, you should also observe CP violation in B decays. Okay, so let me just describe this. Once again, I'm not going to, this is meant to just give you a flavor of this. And so in the standard model, as I say, CP violation is due to this new parameter, this imaginary parameter, that I call I eta. So eta is obviously real. And you can turn this phase information into a triangle relation, in which the interior angles of this triangle are called alpha, beta, and gamma. And these are all related to eta. In other words, if eta is non-zero, alpha, beta, and gamma are also non-zero. And obviously, if eta is zero, then they're all zero.
It's a triangle, but it's something that is not pi.
Sorry?
Some of the angles that doesn't have to be pi.
Well, I mean, if
It's not a triangle, and then you could.
yeah, the sum of the sum of the angles does have to be pi, but
Not be all zero.
but it could be 0, 0, and pi.
You said all zero, zero.
Okay.
Oh, pi equals 0.
Pi is equal to 0 in the sense that it's flat. Right. So the idea then is to measure alpha, beta, and gamma independently, and to see whether their sum is pi. And you also to see whether, if we can measure the sides, see whether everything is consistent with here. And in fact, here's the idea is to measure alpha, beta, and gamma independently, to see whether they add up to pi, and to see whether it's consistent with the sides. And the B factories, Babar and Bell. Babar was an experiment in California at SLAC, Bell was an experiment in Japan. They were built in the 1990s and took data in the 2000s. And they were built to answer these questions. Now, in the late 80s, it was thought that basically that the CP phases could be measured cleanly in these decays. B going to psi k short for beta, B going to pi plus pi minus for alpha, and BS going to rho k short for gamma. Okay, once again, the point is, I'm not, once again, the details aren't important, but the idea was that you could measure these angles by measuring CP violation in these decays. And this was based on the assumption that that these decays are described by so-called tree-level Feynman diagrams, the leading order Feynman diagrams. With Pache, Manu mentioned, with Roberto Pache, we showed that, in fact, there are subleading diagrams, so-called penguin diagrams. Anyway, I'm just going to say that they're loop level, they're subleading. If you want to know why they're called penguins, I can tell you afterwards. Ideally with a glass of wine. Because when you add these penguins, the so-called penguin pollution means that you have to deal with this penguin pollution in order to see whether or not you can actually extract alpha, beta, and gamma. And it turns out that the penguin pollution is very important. So it turns out that for beta, penguins do not pose a problem. So this method of measuring beta is okay. For B going to pi plus pi minus, it does pose a problem. You can't measure alpha after all in this decay. So we showed, Michael Gronau and I showed, that if you combine that information in pi plus pi minus with information in decays to pi plus pi zero and pi zero, basically you make all these measurements and you combine them, and that allows you to eliminate the penguin pollution and get alpha. So this was one of the few things that I've done that was correct. And in fact, this method has become the standard model, the standard method to measure alpha, and was used by Babar and Bell. Okay. The original mode to measure gamma was proposed with BS going to rho zero k short. It turns out that with penguin pollution, this doesn't work at all. This is just wrong. This just doesn't work. So Michael Gronau, the same Michael Gronau and I showed, it was a very productive summer that whenever it was in 1989, I think. We proposed a new method to measure gamma, and that involves these decays: B0 going to D0 K short, D bar K short, and DCP K short, where DCP is it decays to a CP eigenstate. It decays to pi plus pi minus or K plus K minus. Once again, the details are not important, but we proposed a new method. And this method has no penguins, so technically gamma could be extracted. About 8 months later, Michael gave a talk in Switzerland, and Daniel Wieler was in the audience. And Daniel said to Michael, he said, "But this technique, you don't even need neutral Bs. You can use charged Bs." And so they proposed a modification of the method that used charged Bs, but you can see that B plus going to D0 K plus, D0 bar K plus, and DCP K plus. In other words, all the particles have become charged. And this can be used, this can be used just as well, and it's easier experimentally. And in fact, so this method, which has come to be known as the GLW method, is one of the standard methods to measure gamma. Okay, I'm going to quickly go over this one. another topic that I worked on was something called effective Lagrangians. And this is what Manu said. As I said, he stole my punchline. Basically, in the 1990s, no new gauge bosons. They looked at new physics models that had no new gauge bosons that coupled principally to electroweak gauge bosons, and were much heavier than the W and the Z. Peskin and Takeuchi showed that all the new effects could be parameterized by new parameters called ST and U, and those are called oblique corrections. My collaborators, in fact, Ivan McSimic was a student, and Cliff Burgess is at McGill, and so we showed that if you go to next order, okay, so condition number 3 suggests that higher order terms can be neglected. MZ squared over M squared terms can be neglected. We showed that if you relax this assumption, so for example, if the scale of new physics M is light, if you have light new physics, that there are 3 new parameters, V, W, and X. Okay, we wrote this paper, I gave talks, the reaction was, I mean, pretty literally. Okay, now let me fast forward 30 years to today. Now we know we've not found any new physics. So the new physics, if it's there, is heavy. So this is true, that M is much bigger than MW and MZ. But the oblique parameters have been measured extremely accurately. Not the oblique parameters, the observables to probe these oblique parameters have been measured very accurately, to the point where these higher order corrections have to be taken into account. And so now, the effective theory, which includes these higher order corrections, is called SMEFT. EFT is effective field theory, and SMEFT is the standard model effective field theory. All that I want to say is that there's a huge amount of work now done looking at SMEFT and the operators. And so now this paper has been cited a huge number of times as being one of the first ones to probe to probe these higher order terms. And as I say, who would have guessed? Okay, so Manu tells me that I'm basically out of time, correct? Yeah. Okay. So no, that's fine. So I'm not going to go over the other things that I've done. Let me just say that. So all this other thing, I was just going to talk about a few other things that I had done. Let me just say that today there are a number of hints of new physics. Let me just go right here. So in addition to dark matter, neutrino masses, and the baryonic asymmetry of the universe, there are measurements that disagree with the standard model. There's, for example, the anomalous magnetic moment of the muon. Its measured value disagrees with the standard model by 4 sigma. That's a big discrepancy. Mm-hmm. The mass of the W, the experimental value of MZ over MW, disagrees with the standard model by 7 sigma. And there are a bunch of other things. Mm-hmm. So right now, there are a bunch of hints in addition to dark matter, and there are a bunch of real experimental measurements that disagree with the predictions of the standard model. So that brings me to my conclusions. Okay, my entire career has been devoted to the search for new physics. That's pretty much what I do. And right now, there are a bunch of hints in addition, as I said, and I'm undoubtedly biased. It may be wishful thinking, but we might be close to getting at hints of what the new physics might be. Okay, so let me stop here.
Thank you very much, David. Before we go to questions, I have to say that I'm here wearing two hats. I am on the executive of the CAP, and I'm a member of the CRM. So I am here this time to congratulate you today on behalf of the CRM for winning this
Okay.
battle. And I
Thank
forgot
you.
to say that.
Okay.
So now, are there any further questions?
David, you said near the beginning that the fundamental representation of SU3 is 3. What does that mean?
Okay. What this means is that, a Lie group, I should say, a Lie algebra is defined by its generators, and the generators obey certain commutation relations. A representation is a bunch of matrices that obey the same commutation relations. And the size of the representation is the dimension of the matrices. Now, with SU2, once again, I don't know how familiar with SU2, you have certain commutation relations. It turns out that matrices of any dimension, you can find matrices of, there are 3 generators, and for SU2, you can find 3 matrices of any dimension that satisfy the same commutation relations. So there are representations of dimension 1, 2, 3, 4, etc. For SU3, it's more complicated. There's the trivial one where it's dimension 1, where everything is a 0. But there is no set of 8 matrices of dimension 2 that satisfy those commutation relations. The smallest one is matrices of dimension 3 that are 3 by 3. And so that's what I meant, the fundamental, it's the smallest non-trivial basically set of matrices that respect those commutation relations.
Yeah, I think, maybe I'm wrong, that towards the beginning, you said that towards the end, you'd come back to gravity, but you didn't, is it because it wasn't important, you didn't have time to tell us?
No, when I said I'd come back to it, what I meant is that that the absence of gravity in the standard model is an indication that we have to go beyond the standard model. That was all.
I'm just going to ask, can you give an idea of how bad the deviations from the standard model are? I mean, infinitesimal model, 7 sigma.
Yes. Quick statistics thing. When I say that when we do a measurement and we find that it's, the answer is X plus or minus delta X. What this means is that if we do the measurement again, 2/3 of the time we will find the answer between X plus X and X minus delta X. 95% of the time we'll find between plus 2 delta X and minus 2 delta X, 2 sigma, 99, 3 sigma. But so that if a measurement disagrees with the prediction by 1 sigma, maybe you do the measurement again, you'll find that it moves by 1 sigma. That's not unusual. But if you find that there's a disagreement by 5 sigma, I think the probability is 10 to the minus 5, 10 to minus 7 or something like that. So it's kind of like you've got your Gaussian, and the question is how far the tails are. Anyway, all this to say is that when experimentalists say that they have found a signal of something new, they require a 5 sigma deviation. 3 sigma happens, 1 in 100. You make 100 measurements, you're going to find one that disagrees by 3 sigma. So 3 sigma is not, for theorists, we like them, but the experimentalists, they say, no. So there's a whole bunch of 2 sigma effects. And as I say, the theorists get excited, but this 7 sigma, the disagreement of the mass of the W disagrees by 7 sigma. If that's confirmed, that's a big deal. The anomalous magnetic moment of the muon disagrees by 4 sigma. That's a pretty big deal. You know, there's still some questions, and there are the others are smaller. The experimentalists are not terribly excited. And in terms of dark matter and things like that, there's no doubt that there's something funny going on, whether it's actually dark matter or your favorite gravitational changing gravity. That we don't know, but it's yeah.
Again, but you didn't say anything about dark energy, which has been prevalent.
Dark energy, that's not only the reason I didn't say anything is I don't know anything about it, but nobody does. So no, I mean it's in a sense not entirely a particle physics thing, right? Right. It's more cosmological constant, general relativity. That's the likely explanation.
But despite the word energy, dark energy, it's not ruled by equal-MC squared. You cannot transform this dark energy into dark mass or something.
I don't know. No idea.
Okay, I think we should thank David.
Okay.
Everybody's invited to wine and cheese in the